So first we want to talk about something called compound events. Compound events, the first bullet point there is your definition from your textbook, is the union or intersection of two events. And then I like to define compound events on my own by saying it's when you can have two outcomes from a single event. So this is different than what we did last week or what you see on your quiz, where we might be picking two cards from the deck of cards. We might be spinning the spinner twice or selecting 3 students from the class. What we'll work on today is where if you just select one person, one card, one marble, one spin, what's the probability of this or that? So we're looking at two events from the same, two outcomes from the same event. All of these compound events can be classified in one of two ways, as overlapping and disjoint. Last week when we talked about independent or dependent, we were classifying what I would call consecutive events, where we were talking about and then, one right after another. So here we're talking about compound events at the same time. They can either be overlapping or disjoint. What does the word joint mean to you? What's that? Together. So disjoint would mean not together, no overlap. They share nothing in common. Okay, and that will be helpful when we get to the definition. A key word that you can look for in these problems is the word or. So one of the biggest struggles that we'll have going forward in the chapter is when we put 10-2, independent and dependent, together with 10-4, overlapping and disjoint, how do you know which is which? Okay. One way that you can think about it is this, like consecutive versus compound. Are you doing multiple picks of something? Then it's independent or dependent and you should multiply. Or are you picking just a single item and looking for two outcomes? Then it would be classified as compound. It's an or, and we're going to end up adding our probabilities. Okay, so keyword to look for is or. And we're also going to draw a visual of what compound events look like. To do this, I'm going to go back to our Venn diagram. So I'm going to create a rectangle. I'm going to draw 2 circles, A and B. And I'm going to put some outcomes in each of the circles. This is an example of compound events. The compound event is really the whole part of the Venn diagram that is the circles A and B. So we're talking about things that are just fitting in A, things that just fit in B, and then things that might fit in both. So I could say, bless you, I could say event A would be being a female. Event B could be being a sophomore. And there are people who fit in the intersection of both of those. They are both at the same time. Raise your hand if you're a female and a sophomore. Okay, so I've got Riley, okay, and Kylie. So we can put Riley and Kylie here in the middle. Then there are other people who fit just in the female category. Bailey, you're a female, but you're not a sophomore, right? Okay, so Bailey's name can be here. Skylar's name, Faith's name, we can put them in this bubble. And then we've got other people who are sophomores, but aren't females. Do I have any gentlemen who are sophomores here? No sophomore boys? Okay, so we'll make one up, Joe. Joe is a sophomore, but he's not a girl, so he can't be in the intersection, but he can still be in event B. Okay? And the compound event is all of those people in all parts of the circles. In the intersection, in the just female section, in the just sophomore section. Okay, that's everybody. Okay, now, each compound event can be defined one of two ways. So first way we can define them is overlapping. And that's when we have one or more, outcomes in common. I'm going to draw the same visual that we had on the last screen. And what I'm going to do here is I'm going to highlight the actual overlap for our events. So what we have pictured there are two compound events, A and B, and then what I highlighted in the middle, that intersection of the two circles, that of course is going to be our overlap. So some events can be both, like the example that I used, female and sophomore. Okay, there are some people who fit only one category, and then there are others who fit both categories. Now, the second way we can define a compound event is to describe them as disjoint or mutually exclusive, and that's when we have no outcomes in common. The example that we were using before, females and sophomores, that wasn't a good example because we do have the possibility for overlap to exist. Perhaps I could make a new Venn diagram to show a disjoint or something called mutually exclusive. And I would have event A with some outcome, and I would have event B with its own outcome, and there would be no overlap. So kind of stealing from my last example, maybe this is an example of now I'm splitting people into females and males. Okay, you belong in one category, but not really both categories. Or we could take the other side of that, sophomores, juniors. You're a sophomore or you're junior, but you're not both. And I would vote you by like credits, not by years. Okay, to kind of clear up any confusion that people might have. But that we describe as disjoint, and Jackson had said joint means together, disjoint means not together. There's nothing together there. They're totally separate. Okay, I think I have these switched around on your closed notes. So I'm going to do a quick switch right here, just so you can put them in the right places. I'd hate for you to have them in the wrong spot and then figure things wrong. That one. There we go. How about that? So you'll have a 2-column chart, and I like in probability to do lots of 2-column charts where we compare one to another. So I'll just give you some time to jot these items down, and then we'll talk about them. They're just really extra examples to help us kind of be comfortable with the terms disjoint and overlapping. So it's important for us to build our comfort levels with the vocabulary that we use in probability. That will make reading problems and then talking about issues inside of problems much easier for us. And so it's really important that we can understand like what's different about an overlapping event compared to a disjoint event. Overlapping events mean it can be both at the same time. Doesn't have to be both at the same time, but there is that possibility. Disjoint or mutually exclusive means absolutely will never occur at the same time, so our probability there is 0. Okay. Examples of overlapping events: if I pull one card from the deck of cards, what's the probability that it's a face card or a black card? There is some overlap there. You can think of some cards in the deck that are face cards and black cards at the same time. For example, the King of Clubs. Okay. Walking and chewing gum. You should be able to do both of those things at the same time without much problem. You might have a friend that you would not advise to walk and chew gum at the same time. We all know that one person, okay? Or that might be you right now. But overall, those things can go hand in hand. And then the same example I used before, female and sophomore. We already have two examples. We know that those things overlap. So overlap exists, and the probability of A and B is greater than 0. This is interesting because I made mention of this last week when we talked about independent and dependent, because we saw the word and, but I always wrote the word then underneath it because that and meant and then something else, so consecutive event. Here, and means at the same time. So instead of doing another pick, drawing another card, picking another student, something like that, I'm looking for just one student, and what's the probability I get both at the same time? Okay, so we'll have to be very careful with that this and means something different. And then on the other side of that, disjoint and mutually exclusive can't be both at the same time. For example, if you have a bag full of marbles and they're solid colored marbles, I can't reach into the bag, pull one marble out, and have it be green and yellow at the same time. It will be one or the other. Okay. If I'm walking forward and then I'm going to make a turn, I'd have to make a decision. Am I going to turn right or am I going to turn left? But I really can't do both at the same time. That would not be possible. And then the last one there, a freshman and a sophomore, if we vote by credits, at some time you have the correct number of credits to be a sophomore, so you move up in the ranks. And then if you don't, you stay a freshman. So there's no overlap there, and the probability of A and B is equal to 0. So we need formulas. I'm going to give you the first formula for the probability of A or B, and this works for any compound event, whether it's disjoint or overlapping. It works for everything. So if there's one formula you know, it should be the first formula we write down. The probability of A or B is equal to the probability of A plus the probability of B minus the probability of A and B. So remember I said today's keyword would be the word or, and or would imply add your probabilities. If you look back at your quiz, you did no adding of probabilities, you multiplied your probabilities. Because we didn't have ors, we had and thens. Okay. Now the only extra thing here is you do have to subtract overlap if it exists. So if you don't subtract overlap and you calculate probabilities for A and B, you'll have counted some things twice. And then you'll have overcounted and overestimated probability. Okay, we'll look at the first example. We'll see how that could happen. There's a second formula that we can use. It's for disjoint events. Can you look right above in your notes to that 2-column table? What did we say about the probability of A and B at the same time if the events are disjoint? Feel free to just shout it out. It's just equal to 0. So if A and B are disjoint, we could have a simpler formula where we just add the probability of A plus the probability of B. Do we have to worry about subtracting overlap for disjoint events? No, because no overlap exists. So we could simply write it as the probability of A plus the probability of B. Now, if you can recognize a disjoint event, I'm all for using that simplified formula. But in the event of like you're feeling a little bit confused about all this probability stuff, I want you to put your focus on that very top formula and always think about subtracting overlap. And then if you don't have it, you don't have to worry about it. Okay, we're going to put this formula to use, the probability of A or B. And we're going to talk about example 1 at the bottom of the front page, which is, what's the probability you reach into a deck of cards, you select a card, so a single card, and the card is a face or a black card. Since I'm reading this problem, and I see the keyword or, I immediately think about that formula we just wrote down, and I'm going to rewrite that formula, but instead of using A's and B's, I'm going to assign my two outcomes. So I'm going to write face wherever I see A, and I'm going to write black wherever I see B. So I'm going to rewrite that formula. The probability of a face or a black card is equal to the probability of a face card plus the probability of a black card minus the probability of a face and a black card. One way to check that you've got the right formula, just reread it with A's or B's and make sure it says the same thing as our formula up at the top there. The probability of A or B is equal to the probability of A plus the probability of B minus the probability of A and B. Okay, so I just filled in different outcomes instead of A and B. Now, figure out like what it is you're trying to answer and what it is you should be able to fill in. So they're asking us, what's the probability of selecting a face or a black card? So this is what we're trying to find. So I want to know this probability. If I give you that information, you should have enough knowledge, or I'll provide you the information you need to get the other three probabilities to make this happen. So we'll work together since some of us are better at cards than others. What's the probability you reach into the deck of cards and you get a face card? 12 out of 52. Okay. The face cards are jacks, queens, and kings. So there's 3 face cards in every suit, right? Diamonds, hearts, clubs, and spades. So there's 3 of each. 3 times 4 is 12. Okay, so 12 out of 52. Add that with the probability of selecting a black card. 26 out of 52. So half the deck is red, half the deck is black. 52 divided by 2 is 26, so we'll say 26 out of 52. And in this group, we counted all the black cards, like the ace, the 2 through 10, and the jack, queen, king of clubs. We're counting the ace, the 2 through 10s, and the jack, queen, king of spades. But the problem is, we already counted that jack, queen, king with the face cards. Okay. So what that means is, I counted the jack of clubs twice, counted the queen of clubs twice, the king of clubs twice, and the same is true for all those face cards in the spades. But those cards only exist one time in the deck. So now it's my responsibility to subtract overlap. How many cards are face cards and black cards at the same time? 6. We've got 12 face cards. Half of them are red and half of them are black. We've got the jack, queen, king of clubs, and the jack, queen, king of spades. So we have 6 cards that were counted in both of them. So we have to subtract 6 out of 52. If I don't subtract 6 out of 52, I counted them one too many times. Since these all have common denominators, I can keep my 52 and just work with my numerators. 12 plus 26 is 38, minus 6 is 32. And then I can either simplify this, these both divide by 4, or divide it in my calculator and get a decimal. Does anybody have the decimal value for that? 0.4 Did you get 8 out of 13? 32 out of 52? Somebody with a calculator help me out. 0.615. Or you could say 61.5%, and if some of you like to write percents, that's fine. I want you to jump ahead to example 3. Could you work on example 3 for me? Okay, read it, think about it. If you want to write out the first line like I wrote, you can. Okay, example 3, a weather problem. No, this is a person. This is a person who this is something you know about. So it focuses. Lean over, tuck to your shoulder buddy or small group of people around you. What did you do? What is your answer? Have that discussion real quick for me. Cole, what'd you get? No, talk.
I got 40%.
40%. Raise your hand if you agree with 40%. 1, 2, 3, 4, 5. Riley, what'd you get?
I don't know.
Okay, what was troubling to you?
Like which ones to put in first.
Okay, which one to put in the different probabilities? So one thing you can do when you're first starting out problems like this is exactly what I did in the last example, which is assign A and B and rewrite that whole statement, but put the words in instead of A and B. So we're saying the probability of rain today is 20%. Someone call A today. And the probability of rain tomorrow is 30%. Someone call that B. And it says the probability of rain today and tomorrow is 10%. What's the probability that it will rain today or tomorrow? So I've still got that keyword or, which tells me to use my compound formula. So I could write something out like the probability of today or tomorrow is equal to the probability of today plus the probability of tomorrow minus the probability of, and for shorthand purposes, I'm going to say both. I'm going to erase Cole's answer here just really quickly. And then you just have to go back and you have to reread. Which parts do you get? The probability of rain today is 20%. So I'll put that under today. The probability of rain tomorrow is 30%. So I'll add that. The probability of rain today and tomorrow is 10%. So do I put it on the left side or the right side? Right side. It's the and, it's the overlap, it's the both days. So minus 10%, and then my probability of or is 50 minus 10, which is that 40% that Cole gave us. Thanks, Cole, for offering up your answer. Okay, now if we go back to example 2 is going to work differently because we're not going to solve for the or. We're going to solve for a different part of the problem in number 2. So if we go back to number 2, it says, a survey of 200 pet owners. 103 own dogs, 88 owns cats, 25 owns birds, 18 owns reptiles. That's a lot of information. We're going to sift through that information, but before we do that, we're going to figure the setup of our probability. Okay. Of the respondents, 119 owned a dog or a reptile. Keyword is or. So I immediately know to use that formula on the front side of my notes for compound events. What's the probability they owned a dog and a reptile? Okay. Now, before I go into answering the questions, I'm going to do just like I did on the last two problems. I'm going to just fill in A and B. Okay, so what could we call event A? Justin, an idea? A dog, that's perfect. We'll call dog be A and reptile will be B. So I'm going to write this out. And I'm going to use D and R, just because I don't want to write everything. The probability of a dog or a reptile should be equal to the probability of getting a dog or having a dog plus the probability of having a reptile minus the probability of, and you can say D and R, but I'm just going to say both here, okay, at the same time. In the beginning, this can be a really helpful step to kind of fill in the words, and then you can go back and try to fill in what you know. Okay. So, what numbers or which probabilities can you figure from all the information they give? The what one? The dog plus the reptile. What do you mean dog plus reptile? The both?
Same, kind of probability of the dog plus probability of the reptile.
Oh, you can find these separately. Is that what you're saying?
Like,
What is the probability of having a dog?
it's 103.
Okay, 103 over 200. And the probability of owning a reptile? 18 over 200. And we could add those together and get 121 over 200. Okay. There's two other things we have left. The probability of or and the probability of and. Right? The both at the same time. Which other one do we know? If you read the problem. It says in the second line there, of the respondents, 119 owned a dog or a reptile. So we could say 119 out of 200 belongs in my or spot. Which normally we left that spot blank. So this one works out a little bit differently. There goes. Down. So then on the other side here, I can just say minus the probability of both, minus the probability of both. Okay, that's our unknown. Can you tell me what the probability of both is just by looking at that equation? What must you have subtracted? You could solve, okay, so you want to subtract 119 over 200 from both sides?
Yeah.
Okay, you could work to solve it algebraically. 119 over 200 minus 119 over 200. And this will give me 0. And then 121 minus 119 is 2 over 200 minus the probability of both. Okay, and then you could do another algebraic step, which is add the probability of both to the other side. Okay, you could do that. So those cancel out, and we come up with something like the probability of having both a dog and a reptile is 2 over 200, which reduces to 1 over 100, or 0.01. So I think we have our answer. Now, I want to put out one final message to you. Jackson used algebra, and I think that's great, because then you're always going to get the right answer.
Please pardon the interruption. At this time, please release all ninth grade students to the theater for the ninth grade team competition. Ninth graders, please try to sit in your teams when you enter the theater. Again, please release all ninth graders to the theater for the ninth grade team competition. And ninth graders, please try to sit in your teams when you enter the theater. Thank you.
Could anybody get the answer 2 over 200 without having to do those extra 2 steps? Bailey, tell me how you thought about it.
I just did like 103 over 200 plus 18 over 200 minus 419 over 200.
Oh, okay, so you went up right up here and you said 103 over 200 plus 18 over 200, and then you subtracted 119 over 200. And you got the same answer, 2 over 200. And I think that you're kind of doing what Jackson is doing, but maybe you're not writing it out as algebraic steps. Okay, good. Did anybody else think about it differently than Jackson and Bailey? I want to put the power back in your hands. Like, you of course can use algebra, but I also like Bailey's method, where she's just kind of thinking about it logically. Or, like some of you, if you go back to this line right here, is 119 over 200 equal to 121 over 200? No. What would you have to subtract from this fraction so that they are equal? 2 over 200. I mean, you can just reason through it that the probability of both has to be 2 over 200, because these things have to be equal. Probability should be a chapter where you can think outside of the normal algebraic box. So don't be afraid to do that when you're working on homeworks and things like that. You do have to make sure that you're